this is purely if you want to, but next Tuesday night, looking at the forecast for next week, that's about the only night it's gonna work. So Tuesday night, 7 o'clock, I haven't even had a chance to play with the telescope, so it's kind of gonna be a cool deal for everyone involved. But anyway, so if you want to, because at that point, we'll be talking about planetary motion and stars and what you can figure out.
I'm trying to set a reminder. Telescope night on Tuesday, November 1st at 7 p.m.
Why are you saying
I'm good.
Taught for 30 some odd years, never had that happen. Now.
It's a smartwatch.
Okay. I'm not smart enough to operate. That's why I just got this.
You should get an Apple Watch.
No.
I have
I
that
love
feature.
them.
I have that feature on mine. Look,
What?
I have that kind of
Like the hand.
layout.
The
Yeah.
manual? Is that what it's called?
Yeah, look.
Old,
guys,
old
like, read
school. How about that?
I don't know how to
about
read
old school? So, anyway. So well, that'll be kind of a cool deal. So something to think about. All right. So let's talk about, speaking of planetary motion, let's talk about number 7. So here's our star. Here's the Earth coming around like this, okay? And we're actually what's known as what's technically called the Goldilocks zone in planetary motion, because we're not so far away that the waters all freeze on the oceans. We're not so close, we get so warm that the water all evaporates, so we're kind of right in the sweet spot. And we also, the other thing that happens is that allows us to have an atmosphere, so we have a strong enough gravitational field to hold an atmosphere. Like the moon doesn't have one, Mars doesn't have one, because they had one before, especially Mars, because they had weather. But they lost that atmosphere. Part of that reason is because they don't have a strong enough gravitational field. And as a matter of fact, NASA just came out with a report yesterday that said they thought, the number of planets or exoplanets that they think might be favorable for life to develop has shrunk drastically because of the fact that they thought they might find planets orbiting what they call dwarf stars, and they might be like, in that Goldilocks zone. And the problem is they're so close to these stars, and these stars are emitting so much radiation that the radiation is going to blow away their atmospheres, and without an atmosphere, you don't have life. So more and more, we're finding out that we are not one of many, but we're actually one of very, very few where this happens just right, that there's so many things that happen, which we'll talk more about. So anyway, so you have, no thanks, go away. So does the sun, well, obviously the sun creates this gravitational field, which we'll talk about more later. So the Earth is undergoing centripetal acceleration. How do you know it's undergoing centripetal acceleration?
Because it's in a circle.
Moving in a circle, right? If it wasn't undergoing centripetal acceleration, what would it do?
Go straight.
Move off in a straight line. So we're falling towards the sun. And everybody goes, oh, that sounds horrible. We're falling towards the sun. We must do something. Okay, no. We want to fall towards the sun. Because if we're not falling towards the sun, we're screwed. That's cold hard reality. So what you're trying to find basically is the rate of change in that velocity vector. But we're not talking about a rate of change in the magnitude of it. We're talking about the rate of change in the direction of it. So basically, this vector is continuously being pulled in. So here's the simplest way to do this. Your centripetal force, or your centripetal acceleration is 4 pi squared r over t squared. You can go through and you can find the velocity, and then you can use v squared over r. Don't, okay? You can do that, but I don't recommend it, because you're just going to go through a lot of pain and suffering when you could just do it all in one equation. Here's typically what you forget to do, is that you forget to square pi, okay? Because you're not used to that. Oh, circumference, 2 pi r. Oh, area of a circle, pi r squared. You aren't used to that methodology of squaring pi. So watch that. So that answer should be something times 10 to the negative third, okay? Pretty small accelerate, and that's okay, okay? We want to accelerate, but we don't want a huge acceleration either, or otherwise you tear the earth apart. On number 9, every answer on number 9 should start with a 4, okay? Every answer on number 9 should start with a 4. On number 10, with the question about the Mini Cooper going around, both of those answers should be 5-ish, okay? Your answer to number 4 should be around 4, and your answer to number 3 should be around your age.
I liked this assignment.
Okay? Any questions? Going once? Going twice? So, get that in. Okay, so here's what we've got. This is going to be the last thing on purely centrifugal motion. Now, so what we haven't really talked about is the influence of gravity. Because every time that we've done this, all of our motion has been like in a horizontal plane. And as this thing is going around, as you all noted on on that diagram, as this thing is going around, you have a gravitational force acting down, you have a centrifugal force acting this way. Okay, that's it. There's only 2 things in town. And as it goes around, that tension stays the same because everything is staying the same. The force is acting outward. It's not a big deal. But what if I did this? What if I take this rubber stopper and I swing it in a vertical loop like this? Okay, now, if we assume that the velocity stays the same, now I'm just talking about the magnitude, okay, the speed, however you want to think about it. If that stays the same, when would this string be most likely to break? Would it be most likely to break at the bottom, at the top, or on the sides?
Bottom.
How many vote bottom? Okay,
Wait. Yeah.
yeah?
Hmm.
Huh? How about side? How about top? Okay. Why did you all vote bottom? And the answer is right.
Oh, force of gravity.
Sam?
Wait, I should know. Somebody else answered.
No, you raise your hand.
You answered. Wait. Well, I was thinking wrong because I was gonna say it's because it's undergone the most like vertical acceleration from gravity when it reaches its bottom, but then I realized acceleration is constant, so not really
It's con.
constant.
Huh.
You know? You know what I'm saying, right?
Yeah, kinda, yeah,
Kinda, yeah.
ish, yeah.
Okay.
Marilla?
I feel like it would break because the net force is the largest because of the force of gravity, and they're acting in the same direction. You know? Force?
Is gravity acting on it when it's at the top?
Yeah.
I mean, yes, but like, it's in.
So is gravity
But there's another vector going upwards, I feel like, you know?
when it's at the top?
Maybe not. I don't know.
There's a vector going upwards when it's at the top.
I mean, it has to get there somehow.
Valid?
But it's going inwards at a 90-degree angle, so then. I thought
Okay,
that's what you said.
let's just,
I don't
let's
know.
play a couple of scenarios. Okay, let's just play a couple of scenarios. Scenario number 1, I'm just holding it like this. Okay? Is there tension in the string?
Yeah,
Which direction is that going to act?
inwards.
Opposite of gravity, right? So how can we calculate, if I'm just holding it, leave everything else out. If I'm just holding it, how much upward force is it going to be? Enough to balance out what? Gravity, the weight of what's pulling it down, right? So if I'm just holding it, this upward force here is going to equal mg, right? It's going to balance that out, true? Okay? You all are sitting in chairs. Chairs are balancing out the force of gravity, right? Now, I want you to visualize this. This would be cool if I could do this. Imagine that I could take this entire room and I could start to make it swing back and forth like a pendulum. Okay? So this room starts to go like this. Okay? Like this. Back and forth. Okay? So have that visualization. Have a second visualization that all of your chairs are equipped with like bathroom scales. And you can sit down and you can get a reading on a bathroom scale. So let's say you're sitting here right now and you look down and it's in newtons, okay? Let's say it's reading 500 newtons, okay? Bathroom scale measures in newtons. And you look down and it's 500. You're just sitting here. You're not moving. You're just sitting here. You look down and it's reading 500 newtons, okay? Now, imagine that we start to make this thing swing back and forth like this, okay? When you get to the bottom, now that we're swinging, okay, what do you think's going to happen to the reading on that bathroom scale? Is it going to be more than 500, less than 500, or equal to 500?
Equal.
More than.
More than, why? When you get to the bottom of the swing, what does your body want to do?
Stay on.
Yeah, no. You get to the bottom of the swing, your body wants to go in a straight line because it has inertia, right? So when you get to the bottom, are you also, in addition to overcoming gravity, what else is that chair making you do? Oh, overcome inertia, okay? So that chair has to do two things. It has to prevent gravity from pulling you down, and it also has to force your body to change its velocity vector and travel in a circle. So when you get to the bottom, that scale might be reading 520, okay? Because it's the sum of two things. It has to overcome the gravitational pull that's pulling it down, so the upward force has to balance that out, plus, and this is where the whole key to this, what's the direction of any centripetal force? At a? To the? So when this thing is hitting that bottom, you have an upward force that's doing two things. That's overcoming the gravitational pull and it's providing the centripetal force to make you move in a circle. So at the bottom, you're going to feel heavy. Now, you intuitively understand this equation, that the total force that you experience at the bottom is going to be the sum of two things. It's going to be the centripetal force to make you move in a circle, plus the gravitational force to overcome the Earth's gravitational field. Now, this is where this makes sense. If you all are just sitting here right now, are you undergoing any centripetal acceleration?
No.
Right now?
No.
No. So what do you feel? You just feel normal gravity. So if I can make this room swing back and forth, then at the bottom, you're not only are you overcoming that typical gravitational pull, plus you would add in the additional force it takes to make you move in a circle. So roller coasters take advantage of that. So let's give that a look. Oh, come on.
I used to watch this.
Now, hold on, let's go back a little bit. So when you're watching this, you're coming down and you're hitting the bottom of this loop, okay? even though it's just a visual, I mean, when I watch this, like I can almost feel it in my stomach, okay? So when you're in this roller coaster, imagine that you are on this roller coaster and you have a bathroom scale that you're sitting on. So when you get to the bottom of that roller coaster, what's going to happen to the reading on that scale? It's going to increase. Because think about this, if you're just sitting there, if you just stop at the bottom, oh, great, this is how much I weigh. But when you get to that bottom, your body wants to move in a straight line. So not only are you overcoming that gravitational pull, then you're going to feel heavy because you want to move in a straight line. So it's adding that together. Now, the opposite happens. When you go up over the top, what does your body want to do? Yeah, your body continuously wants to move in a straight line. So when you get to the top, you're actually going to feel a little bit lighter because your body basically wants to go away from the path of that roller coaster. So keep that in mind. So, you all intuitively understand this equation. Hey, just on that roller coaster. So when you go to the bottom, you're going to feel heavy. When you go to the top, you're going to feel light. So here's your two equations. When you're at the bottom, and that's all we're going to feel, we're just going to deal with these two extremes. The total force that you're going to feel is going to be Fc plus Fg. At the top, what you're going to feel is you're going to see Fc minus Fg. Okay? So here's the deal. Visualize this. So if I'm swinging this thing around, okay, like this, if I'm going fast enough, there's tension in the string, and it completes the loop. But if I'm not going fast enough, then I don't complete the loop. But if I'm going faster, then I do. So if I'm too slow, that happens. If I'm faster, the string stays taut. So what that tells me is that there's a minimum velocity that I have to complete this loop. Because if I'm too slow, I don't complete it. If I'm fast enough, I do. So there's a break point. So what we're going to do is that we're going to take, this is only going to happen at the top. So what we're going to do, we're going to go to the top, and this is, remember this on all these problems. That total force is what you are going to feel, okay? Like right now, you all are under 1G. You all have lived your lives under 1G, okay? Now, well, like we talked about though, if you're like in the spinning teacup or whatever, okay, when you're going around, oh, you're going to feel heavier, right? So that total force is what your body experiences. So one scenario is that you let that side equal to 0. You are going to feel weightless, okay? So in other words, you're at the top of this flight, you are going to feel completely weightless. So that's going to equal force centripetal minus Fg. So because we're subtracting, I can move the Fg over here and go Fg equals force centripetal. So what this means, and this is important, if you want to be in a state of weightlessness on Earth, you want to be in a situation where the gravitational force acting downward at the top is providing the exact centripetal force that you need to complete the loop. So, how do you calculate Fg? Oh, that's simple. That's mg. How do you calculate centripetal force? That's mv squared over r. Okay. Now, conveniently, what happens to the mass? Cancels out. I have mass on both sides. It goes away. So this is what I call like the canine equation. So if I solve for velocity, I'm going to multiply by r. And then take the square root of that, and I get GR. That's why I said it's like the canine equation. Okay? So what this tells you, if I'm going to complete this loop, what that tells me is the minimum velocity that I have to have to complete that loop. So if I'm going faster, I need the string. If I'm not going fast enough, I don't complete the loop. But if I can hit just this velocity, what that would mean is that that rubber stopper would complete this loop, and I wouldn't need the string at all. It would just make that loop on its own, because gravity is providing just the enough centrifugal force, which is oddly enough acting downward towards the center of the circle, to complete the loop. Now, grab the camera. Let's go back towards the roller coaster.
Action.
Action. Okay. So, you got your basic roller coaster. We talked about this before. So, I come up here and start this. Boom. Oh, that's it. Well, there's Timmy. Yeah, Timmy's gone. Timmy's a goner. Okay. So, notice with that one what happened. Didn't go fast enough, right? But if I go faster, crash and burn. Okay? We go all the way around. So it should go a little bit faster, hopefully. Oh, come on. So that one, notice it stayed in contact with the track all the time. So if you're an engineer, when this thing hits the bottom, that's where it's going to require your most load. Because if you think about it, when this thing comes in and it hits this bottom, again, it's this whole idea. Gravity is trying to pull this thing down, so it's got to counterbalance that. And when it gets to the bottom, this thing wants to move in a straight line. So you have to provide two forces. You have to overcome the force of gravity, and you have to force this thing to travel in a circle, which it doesn't want to do. So this would be the ultimate roller coaster, okay? Not an insurance company in the world would touch you, but this would be the ultimate roller coaster. And you could call it the 0G roller coaster. So if you go back to that equation, V equals the square root of GR. That tells you the minimum velocity that you have to have to complete a roller coaster. So if you knew the radius of this loop, you could calculate the minimum velocity it would have to complete that loop. And if you knew you could hit that velocity every time, you could take out the top section of this roller coaster. So people show up and it's like, oh, it's missing the top loop. Okay? And that's because for a brief period of time, you would be in a state of weightlessness. Because gravity is providing just the force that you need to complete that loop. But here's the problem. If you're going just a little bit too slow, that's not going to end well. If you're going too fast, when you get to this point, you'll overshoot this structure, and then you're going to run into that side. That's not going to end well either. That's why I said it's a great thing in theory, but that's why I said no insurance company in the world is going to touch you because of the fact that it would have to hit just a specific velocity. So again, visualize this. You get on the roller coaster, you're wearing a trench coat, which sounds odd. Worse yet, you're carrying a bathroom scale. You get in, you sit on the bathroom scale, you look down, you can get away with it. I'm a physicist, back off me, okay? I'm doing an experiment video. Okay, ooh, all right. So you look down, wow, you're reading 100 pounds. You're traveling straight and level, it's going to stay at 100. But when you're at the bottom of that loop, what's going to happen to the reading on that scale? It's going to go up. You are going to feel heavy. When you reach the top, you are going to feel light. Because now, so here's the basic idea, is that if you want to make that safely through that loop, okay, you want, listen to me, and we'll go through the math on this. If you want to safely complete this loop, when you subtract those values, you want that to be greater than or equal to 0. You actually want to design it going fast enough so that you do need this top structure. So basically what happens, you want so much centripetal force that gravity can provide part of it, but then this structure up here is going to provide the difference. So you want to be going fast enough that you have to have this. Now, some of those rides, they'll design it where you come up over the top. Now, the beauty of going up over the top is that if you're not going fast enough, the structure is still there to catch you. So if you go up over the top, you just have to be going fast enough to go over it, okay? There is no minimum velocity other than going fast enough, because if you're not going fast enough, oh, the structure is there in effect to catch you. You're still going to get that sensation of feeling the light, because when you come up over that top, your body wants to turn into a projectile. Your body continuously wants to go in a straight line. So with that bathroom scale, it's still going to read less at the top because your body continuously wants to go off in a straight line. Okay, back we go. Is what happens to your body when you, on Earth, we can simulate this idea of weightlessness or zero gravity. So they're going to talk about a plane called the Vomit Comet, and that's actually what it was called. So what they did is they went through and they said, okay, we're going to take this plane and we're going to fly it into an arc. So basically what they did, oh, come on, go away, is that they went and used this equation. They said, okay, when this plane flies up over the top, you want to experience a state of weightlessness. So they said, okay, if we know the radius of this arc, that tells us how fast that plane has to be flying, so that when you're at the top of the arc, you can feel a state of weightlessness. Now, what they do is you can actually simulate different gravitational fields. So if you go to the top, and we'll do this math here in just a second. It's force centripetal minus Fg. Here's the whole key to this. That force total is what you experience. So one of the things you'll see is that they do Martian gravity. Okay, the first thing they do in this flight, you'll see this, they do Martian gravity. Martian gravity is like 1/3 of Earth's gravitational field. So if you go to lift, if you're on Mars and you go to lift your arms, it will only feel as third as heavy as it does right now. Okay? So what you would do is you would set this equal to 1/3 Fg, equaling force centripetal minus Fg. Okay? This side here is always going to be a multiple of what you experience. So they're going to go through and they're going to simulate Martian gravity. So you would feel 1/3 of what you feel right now. So the math becomes pretty simple. I'm going to move this Fg over here. I'm going to add that. So when I take 1/3 Fg and add it to an Fg, what do I get? Oh, this becomes 4/3 mg equaling mv squared over r. Guess what? Masses cancel out. You get v equals the square root of 4/3 GERD. Right? So now the pilot has to say, okay, if we want Martian gravity, this is a new calculation in terms of how fast that you have to fly. They're going to do lunar gravity. Lunar gravity is 1/6. The only difference is instead of 1/3, you're going to put in 1/6. This becomes 7/6, slightly different equation. And the last thing they're going to do is they're going to put this guy into a state of weightlessness, where this side over here becomes 0, and then it's just the square root of GERD. So, with that said,
Of space exploration, NASA developed a technique to recreate zero gravity, the notorious Vomit Comet. Because the weightless effect of microgravity is nothing more than a continuous free fall, It's possible to simulate it by flying an aircraft in a huge arc or parabola, which, for short periods of time, allow those on board to float as though in space. But the stomach-churning ride could spell trouble for some people. All right, I know what you're thinking. Into another flying machine, and into another stylish flight suit.
So this company is
I joined a group
based out
of
of
eager
Vegas, it's called
participants,
Zero
including
G.
entrepreneur and astronaut Richard Garriott, one of a new breed of self-funded space tourists. This is one of the only privately funded training facilities, offering the public a rare opportunity to cheat gravity in this specially modified Boeing 727. Once in the air, we climb up to 7,300 meters to start the first of 12 parabolas.
Here we go. This very first parabola is going to be cartoon gravity.
So they set that side of the equation into 1/3 mg.
I can immediately feel myself detaching from the floor of the plane.
Like a strongman. 1 arm push-ups. Okay, lunar gravity.
So this is 1/6.
Just let your body flow. Go up, enjoy what it feels like. Just feel your body completely relaxed in the air.
The parabolas are becoming increasingly severe. Basically, I'm skydiving inside the aircraft.
That is so strange. Oh, wow.
Go Team Silver!
This weightlessness thing is pretty cool. You only get short periods of time, maybe 20 seconds, 30 seconds at a time, but it's just like being in space.
We're all going to be facing that way, right? You're going to kneel, and you're going to try to crawl as fast as you can, okay? Okay? All right, so...
Yeah, sure, okay.
Go! Woo!
I can now better understand how difficult it must be to relearn every physical task during a prolonged spaceflight.
Okay. That is just the most unbelievable experience.
We're now completely weightless, able
So
to
now
fly
they've
like
set it
Superman.
into 0.
The constant pitching of the aircraft is pretty intense, and by parabola 10, the effects are starting to hit me.
Okay. Nobody wants to see him throw up.
Remember,
Certainly I don't. That's why I don't do biology. Okay. So, if you ever seen the movie Apollo 13, where they have like Tom Hanks and they sit like inside the capsule, that was all filmed in 20 to 30 second increments. So they took a plane like that, a jet. They built basically the capsule inside of it. And so in those weightlessness scenes, that's what they were doing. They were flying up over the top of that parabolic curve, and you would experience literally at most 20 to 30 seconds of weightlessness. Now, this is why it's called the vomit cone. Because what goes up must come down. So if you go from a state of weightlessness, then at the bottom of that curve to feeling really, really heavy. And then you're going back to a state of weightlessness, and then back to a state of really, really heavy. And some people's stomach tolerate that better, others not so much. Hence the term, the vomit cone. Okay, so here's what I want you to get out of this. If you're at the bottom, okay, you add them together. Force centripetal plus Fg. Add at the bottom. If you're at the top, you subtract. Now, here's how you can use this. So here I've got right back on? There you go. Okay. So here I've got a cup of water, okay? Right? I'm going to put this on here, and I'm going to swing this thing around so that I stay dry. So I want to calculate the minimum velocity that I have to keep this cup from falling down on me. So because I want the minimum velocity, and I'm going to be at the top, I'm gonna use FC minus FG, and you solve that, you get V equals the square root of GER, okay? So, Cooper, ballpark the radius of my arm in meters from here down to there. Ballpark.
1.5.
Okay, so assuming that that's 1.5 meters, so there's my shoulder, boom, boom, there's the cup. Horribly drawn, but you get the idea. Okay, this is time, okay? Here, better, there's a stick, more realistic. Okay, so it's gonna go around like this. So if I want to calculate the minimum velocity, I'm just going to use this. So somebody take the square root of g times 1.5 meters. Now, if you look at what happens with the units, you get meters per second squared times meters. You get the square root of meters squared over second squared. You get velocity. Here we go. So what do you get? What'd you get? 3.83 meters per second. So if I'm going to stay dry, I have to be going faster than 3.83 meters per second. If I'm going exactly 3.83 meters per second, that cup would be in a state of weightlessness. If I'm going less than that, I'm going to get wet. Okay? That's the math. All right. So we do this. You might give that a little bit of a spin. Okay. Trying not to hit anything. Okay. Here we go. All right? So, because that's staying on there, true or false? True or false? It stays on there because up there at the top, it stays on there at the top because there's an outward force pushing it in that direction, which is stronger than the gravitational force pulling it in. Eli, you shake your head. From the get-go, you were like, no.
You said outward? No, there's no.
I agree.
Not there?
No.
Yeah. I can do many things, but what I cannot do is I cannot emanate a force field pushing the cup up. Okay? Would be cool if I could, right? Impressive. Like, what's your superhero strength? I emanate my own force field. Right? I do. So, but why does it? Here's what I want you to see. It doesn't fall because the fact that it's going fast enough that gravity is providing some of that centripetal force. But I need this platform. So that platform is just keeping this thing from traveling off in a straight line. It's just going fast enough. So imagine that we could take like a little digital scale and put it on here between the cup and this platform. That scale would be reading at a maximum at the bottom, but as long as I'm dry, that scale would still be reading something up at the top. So what that means is that that platform is what's providing that additional force to make it travel in that circle. Okay. That's vertical motion. Now the stock horizontal motion like this. So, has anybody ridden, I know this, they've got this right up in Kansas City. It's a spinning barrel, and you stand up against the wall.
The bamboozler.
Yeah, or and they drop the floor. Okay, you ridden this? Okay, so what do you all? What was your experience in riding that?
It's horrifying.
Horrifying. Okay, okay. What did you feel when you? If you're not familiar with this, so imagine, if you will, that you've got this big barrel and it's spinning, and you're like against the side like this. Okay, right? Pretty close, right? Up to your face is doing this. And you're trying like this, your head's like, okay? And then they drop the floor out. So you're like stuck up against the wall, right? So visualize this. Here's this barrel, and you're inside of it like this, okay? So let's look at like a side profile. So here you are. You're like this, okay? There's the barrel. there's three forces acting on you once that barrel wall, once they drop out the floor. What's one of those forces? Gravity. Gravity is still trying to pull you down, right? Gravity doesn't care that you're spinning. And that's still going to be, guess what? mg. Okay? Now, so now we're going to take this. I'm not going to use the water for obvious reasons. I'm going to put this on here, and I'm going to spin this thing in a horizontal circle. Okay? So I'm spinning in a horizontal circle like this. Okay? Now it stays, but if I slow down, it falls. Why are you all spinning? This is weird. Okay, so if I was going fast enough, the rubber stopper stuck there. But if I slowed down, what happened? Began to fall. Which leads us to a couple of options. One explanation is that the faster I spin, that counteracts the effect of gravity. Gravity just doesn't pull as strongly as if I'm spinning. But as I slow down, gravity gets stronger and stronger and stronger, and that's what makes it fall. Sound logical? God, no. Horrible. Stop. No. Okay? Here's the analogy that I would make. If you rub your hands together, let's say they're just barely touching. Okay? Right? They're barely touching. There's a little bit of friction, but there's not much, right? Now, the harder you push your hands together, what happens to the amount of friction? Oh, it increases. Oh! So, might friction be a part of this story? I think friction can be a key part of this story. So, which direction, spinning around like that, which direction is gravity trying to pull you? Downward. So, which direction do you think friction is acting? Oh, friction's acting up. That's kind of cool. Okay? Now, if you're not going to fall, what do you know about the frictional force relative to the gravitational force?
Greater than or
Well, at a
equal to-
minimum, it has to
Equal
equal it. Hopefully, it's going to be bigger. So there's two forces. Gravity, force friction. What's the third force?
Centripetal.
Ah, which direction is the centripetal force acting? Oh, the centripetal force is acting inward. Okay? So, this rubber stopper, as it's going around, or Albert Einstein, whatever it is, okay? So here's Al, we'll use Al. So, as Al is being swung around like this, there's three forces.
That's actually funny.
Gravity, ironically, is trying to pull Al down. The frictional force is keeping Al from sliding in that direction. And then the centripetal force provided by the platform is acting inward. So, as you go faster, what happens to the amount of that centripetal force? It increases. Now, here's what I want you to answer. Imagine you're inside the ride, and you're like this. That would have been awkward. What happened to you told me? I don't know. I was just lecturing and it just fell. Go figure. I don't know. Okay. So, you're like this. All right, I'm not pushing on the television. You're like this. Are you being pushed, because you're Bubba, and you're riding the barrel of fun? Are you being pushed up against the wall? No. Does it feel like you are? Yes. Why?
It's like the car thing.
Yes.
What's it?
What does your body want to
Inertia.
do?
That's what it is.
Your body wants to travel in a. So you're feeling the action-reaction of the barrel wall. There is nothing inside the ride pushing you up against the barrel wall. It's not there. There is no magical, you got Bubba running the ride going, turn on the force field, okay? And then all of a sudden you feel, oh, right, and that's what, no. Because imagine that you could going around in this, and all of a sudden the barrel wall just disappears. Bad things are going to happen. Because you go from centripetal motion into projectile motion, okay? Your body immediately travels in a straight line. So all that barrel wall was doing is you're basically running into the barrel wall. And the barrel wall is going, nope, sorry, we're not going to let you move in a straight line. So here's where the magic happens. Mu equals force friction over force normal. True? Standard definition of the coefficient of friction. True? Now, here's the magic. What does the frictional force have to equal to keep you from sliding down? Has to equal your gravitational force, right? So that has to equal Fg. Now let's talk about the normal force. Whoa, come back here. If it's like this, and it's flat, which direction does normal force act? Upward. Now, if I'm like this, and swinging it around, normal force is acting like this, right? Well, what's providing that normal force? The centripetal force. So the centripetal force, because we're like this, is the normal force. Oh, that's kind of cool.
Wait,
So that's going to be our centripetal force. Now, how do you calculate your gravitational force? Oh, guess what? That is mg. How are you going to calculate your centripetal force? Mass times your centripetal acceleration. What happens to your mass? Cancels out. Oh, so what you have is mu equaling g over ac. Now, so this is where you can. This is what you can do with this. Let's say the typical coefficient of friction. Leslie's on the right, and we know the coefficient of friction between Leslie and the wall is, say, 0.4. Pick a number. So we know this is 0.4. And that's g over ac. So could I calculate the centripetal acceleration that you're experiencing? So what does that look like solved for ac?
G over 0.4.
Multiply by ac, divide back by 0.4. So I'm going to get ac equals g over 0.4. So somebody take 9.8 and divide that by 0.4. What'd you get? 24.5 meters per second squared. So that's the minimum centripetal acceleration that she would have to experience to keep from falling down. Now, this is why you feel heavy. Take that answer and divide that by 9.8. If you divide that by 9.8, now you can talk about G's. So you divide that by 9.8, what do you get? What'd you get? 2.5. So what that means is that if you're inside this ride, you're going to be pulling 2.5 G's. So this is why it feels heavy, okay? You feel heavy because you're undergoing an acceleration 2.5 times that of your normal gravitational acceleration. Now that you have that centripetal acceleration, you can do some cool things with that. So you know centripetal acceleration equals v squared over r. Oh, okay. Now I know what that centripetal acceleration is. If I know the radius of the barrel, okay, let's say the radius of the barrel is, I don't know, 4 meters. If I know the radius of the barrel is 4 meters, then I can figure out how fast that barrel has to be spinning to produce that amount of centripetal acceleration. So if I take AC times R equals V, so somebody take that centripetal acceleration of 24.5 meters per second squared times the radius of 4 meters and then take the square root of that. Should be around 10.
9.89.
9 point what?
89.
That's pretty close. Meters per second. So what that means is if you're on this barrel wall, at a minimum, you have to be going about 10 meters per second. So if we take Al, and we'll sacrifice Al on this one, okay? All right? So if I spin him around and I'm going fast enough, Al stays up. But if I slow down,
He attacked me.
he did. Don't take it personally, okay? So notice what happened. If I'm going fast enough, there's enough friction created by that centripetal force to hold him on there. as I slow down, it's like you're pushing your hands together, but as I slow down, it's like you're not putting as much pressure. There isn't as much friction. Gravity takes over, you begin to slide. Okay? Got that. All right, stop that. Okay, so let me get you through problem number 1. You're going around in a circle. Okay, we're going to look at both situations, what's happening up at the top and what's happening at the bottom. So notice that you're going to hook this thing up to like a scale that measures in newtons. So the question is that what does the scale read when the mass is moving at 4 meters per second at the lowest point of its circular motion? You're going to take centripetal force, add it to the gravitational force. Now, on B, it says, is the mass going fast enough to complete the loop? There's like 3 or 4 different ways you can answer this question. One option is that you compute the minimum velocity using the square root of GERT. If that velocity is bigger than that number, you're golden. The other thing that you could do as another option, but wait, there's more, is that you could calculate the force at the top, which is going to be mv squared over r minus mg. If that force total at the top is greater than or equal to 0, you'll complete the loop. But wait, there's more. This is mass times centripetal acceleration minus mg. As long as your centripetal acceleration is bigger than 9.8 meters per second squared, you'll complete the loop. Now, don't get weird on this and go, oh, that's minus and negative. No, okay? Do not, this isn't like negative, this is like magnitudes, okay? This is just a straight subtraction. Don't go minus and negative. Don't get weird on me, okay? Don't go weird. Just always use being G as a positive value. Now, when you get to question number 4, okay? You're in a roller coaster, you have a radius of 25 meters, you want to feel weightless up at the top. So on number 4 is brought to you by this equation, that force total equals force centripetal minus Fg. So what's going to happen on number 4, you're going to look at different values that you are going to experience. So weightlessness, you're at 0 Fg. You want to feel nothing. Now, eventually I'm going to tell you when you get to question B, I said at what speed must they be traveling so they feel 1/4 is force weight? So when you get to B, then you're going to go, oh, that's going to equal 1/4 Fg equals force centripetal minus Fg. So what's going to happen on number 4 is that I'm going to change the fraction that's in front of Fg. It's going to get bigger and bigger and bigger. You want to feel heavier and heavier and heavier at the top of this. When you get to number 9, okay, this is relevant for Kansas with wind turbine blades. So the blades spin at 22.0 RPM. What does that RPM stand for? Revolutions per minute. Is that frequency or period?
Frequency.
Frequency. It's an event per unit of time. Okay? Now, what I'm telling you on B, I said if the blade is modeled as a point mass at the midpoint of the blade, how much centripetal force is needed? Basically, what I'm saying on number 9 is that here's this blade. Okay? When you do this calculation, assume like all of that mass is concentrated in the middle of the blade. So your radius is going to be half the length of the blade. So in other words, instead of doing all the computations for all the mass that's distributed throughout the blade, we're going to say, okay, let's just make this simple. Let's assume that we can take that entire blade and make it where it's on average, all that mass is halfway between the center and the edge. Okay, it makes the math exponentially easier. Okay, I'm done. You're on your own.